word. Today we are going to discuss one of the most important fundamental aspect of convolutional neural networks called convolution. So this is a mathematical operation which is done by framework when you are using it. So we have implemented convolutional neural networks in Keras, and we have done image classification, and we'll be talking more upon object detection in later videos. And now we'll talk about this mathematical operation, which is the core principle. And so convolutional neural networks are divided. There are three layers which are commonly used in convolutional neural networks throughout, and the first one is convolution layer, the other one is pooling layer, and the third one is fully connected layer. So if you would have seen my previous videos, I've done max pooling after convolution layer. So we use convolution layers and then we apply non-linearity to it using activation functions like rectify linear unit, and then we use fully connected layers. So we'll talk about convolution in this video. So what convolution layers are really doing? So the initial layers are really focusing upon the primitive features of an image. So if we have an image, the first try would be to detect the edges of the objects inside the image, and then we'll later on layers are going to deep dive into taking out, extracting more complex features out of the image. And as we go more deeper and deeper, it becomes harder for us to visualize, but layers are extracting features, more complex features, which is harder to visualize. So primarily, initially we are going to be detecting vertical and horizontal edges. So this is usage of Sobel filter, and we'll talk about filters in the next slide. And this is what visualization looks like when we are detecting edges. And so let's start with the basic operation. So over this video and later on we'll talk about visualization part. So on the left hand side there's a matrix. So imagine it's a 6x6 image. The asterisk is used for convolution, but in Python this asterisk also used for multiplication purpose. So I'll be in this video, this asterisk would mean convolution. And over right side you are seeing a 3x3 matrix. So this is called a filter. It's in research papers, if you read, some researchers denote it as kernel. So I'll use filter for it. So what we do is we are gonna take this filter and overlap it on the weight matrices. So this 6x6 image, and we overlay upon that filter over that matrix, and then we are gonna be performing dot product. So this is the mathematical intuition. And over here on the right hand side we have a 3x3 filter, and over the left hand side we have a 6x6 matrix. And what we do is we take this filter and overlay on the portion, initial first left hand side topmost portion of the matrix, and then we are going to perform dot product. So topmost row consists of 1, 0 and -1 as its element, and when we talk about 6x6 image, the topmost left elements are 3, 0, 1. So what we are going to do is we're going to do a dot product. So 3 times 1 plus 0 times 1 plus 1 times -1. It doesn't matter on which order you go, you just have to take the dot product respectively. And coming to second row, we are computing dot product of 1 and 1, 5 and 0, and then 8 and -1, and similarly 2 with 1, 7 and 0, and 2 and -1. And we sum it up. We take a summation, and that is which is going to be the output, and the output is going to be 4x4 matrix. You may be wondering how we get an output of 4x4. So the formula is as follows. So it's NH previous minus filter plus 2 times padding. We'll talk about padding later, divided by strides plus 1. So 6 minus 3 plus 2 times padding over stride. So stride is 1 over here, and we are not using padding at all. So 6 minus 3 plus 1. The 1 is for the bias which we are using. And again then we shift this filter to the next row depending upon the stride value of the stride which we are using. And then again we are going to be computing dot product. So 3 times 1 plus 5 times 0 plus 8 times minus 1 plus 2 times 1 plus 7 times 0 plus 2 times minus 1 plus 0 times 1 plus 1 times 0 plus 3 times minus 1, and you do over this again and again over the whole matrix, and you will be getting the output. So this is what our input is and this is what our output is. So remember that as we go deeper and deeper into layers, the dimension of the picture is going to reduce, and the number of filters, which is in this case is 3, red, green, blue, is going to increase, and we don't want to lose features. And because as we go deeper into layers, our image, the dimension of the image is going to shrink, and we don't want to do that, because after certain layers the image would reduce so much. So we use called max pooling. So what we do is, in this layer, in the first images, the input image, then we use a convolution layer, then we apply non-linearity to it, and then we do a pool layer. We'll talk about pooling in just later, just wait for some time. And then we use a fully connected layer, and then after end we use softmax activation function if we are doing multi-class classification. So for mathematical this is the mathematical operation which is being done. We are taking this filter and then we are overlaying it over the entire matrix. In a computer vision application, each value in the matrix on the left corresponds to a single pixel value, and we convolve a 3x3 filter with the image by multiplying its value element wise with the original matrix, then summing it up. So this yellow colored matrix is the filter, and we are taking a dot product of each element wise dot product, and then we are computing the value of the element in the convolved feature, and this feature acts as activation in the next layer. So the next layer will contain the activation computed by the previous layer, which is called as convolved feature in this case. So just to make sure that you understand all of this, I'll show a nice video. So this is how convolutions work. In this case we have our input volume, and there are 3 parameters: previous, height, width, and channels. In this case number of channels is 2, which means there are going to be 2 outputs. First one is called first filter output, and other one is called second filter output, and the number of channels are going to be defined how many outputs are we going to get. And in this case we have this filter is going to be taking the element wise dot product, and then we'll be getting the element of the first output. And note that we, in this case, stride is equal to 1. So stride is defined as the number of rows and columns we are going to skip. On each iteration. And when we have a large image such as 1000 by 1000, and that's 1 million parameters, and its computation is going to be very time consuming, and then we then use stride. And so strided convolutions makes us easier for us to compute. And the output volume is then going to be used by the next layer, which is the activation, which will act as an activation to the next layer. So I hope you understood how convolutions work. Thank you for watching this video. I'll be making more videos which will focus upon fundamentals of CNNs, and there's a whole new section of RNNs which I'm working upon. Please make sure you are subscribed to this channel. Thank you. Talk to you next one.